Dear student, we are now going to begin lectures on machine design part 1. This is lecture number 20 and the topic is shaft coupling. So, this is the first of the lectures on the same topic. Now, couplings are normally used to connect two shafts axially. Now, the shafts are usually manufactured in small pieces in order to avoid the difficulties or disadvantages of transport problem. And whenever they are connected by means of these couplings. Now, there is another device which serves the same purpose. This is known as the clutch. The important difference between the clutch and the coupling is that the clutches are used in order to disengage and engage the shafts frequently, whereas the couplings are used to fasten them together, and this is permanent connections and they are only opened up during replacement or repair or maintenance. So, this is one of the important difference of coupling. Now, the couplings are used mainly to transmit power without any loss. This is now this is what we want to say, that transmit power without any loss, that is very much expected, and second, provide for shaft misalignments. Now, shafts are normally installed without any misalignment, but because of various reasons there will be inevitable presence of misalignments. Now, the misalignments may be of different types. Let us see, suppose we want these shafts to be connected this way. So, this is the ideal situations, two shafts axially connected in this fashions and there is no misalignment. There may be misalignment, for example, one shaft is here. So, this one is ideal. There may be misalignment when one shaft is here and the other shaft, the axis of that shaft is offset by certain distance delta. This is one kind of misalignment. There may be another kind of misalignment, that is, there is one shaft, then other shaft is skewed a little bit by an angle alpha. This is one such misalignment. There may be a combination of these two, that is, a shaft may be there and the other shaft is both angularly misaligned, there is angle alpha between these two axes and there is offset delta. So, there are four kinds of misalignments and those are to be avoided, but normally this misalignment occurs in practice and it is difficult to avoid. Then we have provisions, that is, couplings are to be used in order to provide for end movements of the shaft. Now, the types of shaft coupling. There are two principal types of shaft coupling. One is rigid coupling and another is flexible coupling. As the name suggests, the rigid couplings are couplings without any flexible member. There are different kinds of rigid couplings. We have to discuss four which are the principal types of rigid coupling, namely the first one is flange coupling. This is the most commonly used coupling. The second one is sleeve or muff coupling. The third one, clamp coupling, or sometimes it is called split muff coupling. Then compression coupling. Flexible couplings are of two types. One is coupling with kinematic flexibility, that is, we insert certain members which undergoes rigid body translation or rotation, but that gives a little bit resilience or flexibility in the overall joint. The second type is coupling with resilient members. Now, here we introduce some members which have the flexibility. So, this is inherently a flexible couplings. We are going to discuss in this lecture the principal types of rigid coupling. Now, let us come to few types of flange coupling. Now, flange couplings, you see, these are couplings, again rigid couplings, and the coupling is done by means of two flanges. What you see here is the cross section of such a flange coupling. Here the shaft, and on top of it this part which is known as the flange. It has two sections. One is here, which is a relatively thick part, it is known as hub, and this part which is relatively narrow, then this is known as the flange, and these two flanges are connected by means of few bolts. Now, bolts are arranged equispaced, angularly equispaced on a particular circle. This is known as bolt circle. Here you see the diameter of the bolt circle is d1, the diameter of the shaft is small d, and the outer diameter of this flange is d2, and outer diameter is d and the hub diameter is d2. So, this is a protected type flange coupling. Sometimes we do not have this part, and this is called unprotected type of flange coupling. Now, why these protections? Because you know the shafts they rotate. This is the definite purpose of the shafts. Whenever they rotates, then we need some safety. Suppose something goes wrong, this bolt fails, then it may come out, and because of the large rotational speed, a havoc can occur, and so it may be catastrophic. In order to prevent this catastrophe, that is for the work safety purpose, we give this small extensions which is called the protections. Now, this is known as the protected type flange coupling. Then in some applications, for example, in both propeller shafts where the torque transmission is relatively large, there the flanges are integrally coupled, they are manufactured along with the shaft. So, this flange and shaft, they come as one piece, and they are connected by means of these bolts. Now, here you see there is no nut. This bolt is a special kind of bolt, is a taper bolt, and they make the secure connections. You will also see there are two protrusion here. So, on one side of the flange there is a little protrusions, and on the other side there is a recess made. What are the purpose of that? So, these are called resistors, and the purpose is to align these two shafts. Sometimes other kinds of alignments are also done, for example, by keeping some rings over here on the top of on the surface of the flange. So, these are few kinds of flange coupling. The usual design parameters of flange couplings are given here. D1, as I said, which is equal to the bolt circle diameter. This is roughly taken to be twice d, small d, that is the diameter of the shaft, plus 50 in millimeter, that is 50 millimeter, or it may be 3d. Now, why all this? Because the couplings are now manufactured by different manufacturers, and so we have to come to a standard. So, these are normally the standard follows unless otherwise specified to the manufacturers. There are catalogs available from the manufacturers, and we will have to look up into those catalogs to find out exact diameter, but what you see here are normally the usual diameters or usual dimensions maintained in practice. D2, which is the hub diameter, is 1.5 times d plus 25 millimeter, or it may be twice of diameter of the shaft. Everything is mentioned in terms of the diameter of the shaft. The outer diameter is 2.5 times d plus 75 millimeter, or roughly 4d. Length, which is quite important, it is about 1.25 times d plus 18.75 millimeter. You see this odd figure, but these are standards. Tf, the width of the or the thickness of the flange, which I have told in the last slide, is 0.5 d, and n, that is the number of bolts, which that may be 3 for d up to 40 millimeter, 4 for d up to 100 millimeter, 6 for D up to 180 millimeter. So, these are the usual dimensions which are maintained in practice. Now, let us come to the design criteria of flange coupling. So, these are the two flanges which are connected by bolts. Obviously, the most important part here will be the bolts. There are two possibilities. First one is that there is no clearance between bolt and hole, and there may be no clearance. So, depending upon that, the situations will change. Whenever we have clearance, then we see the failure will be different than the case where there is no clearance. Let us see one by one. Whenever there is clearance, then the bolts there are bolts here, different bolts on the circle, bolt circle, and the main pressure, that is the flanges are connected because of the friction force developed by the normal force, and this normal force is given by the bolt. Let us say there are n such bolts and each bolt is given a tension F. So, the total force on the flange, on each flange will be Nf. Now, assume that the force is uniformly distributed, that is the pressure is uniformly distributed. So, therefore, using the uniform pressure theory, the overall torque capacity will be equal to Nf times mu times this distance, that is the equivalent distance, which is equal to let us say d equivalent, and as we have derived in the lecture on power screw, thus d equivalent is twice third r o cube minus r inner cube divided by r o square minus r inside square. So, this is the torque transmission. Now, this torque transmission will be the same as the transmission on the shaft, and if you use this formula, then you get F. Now, F is related to AT, or let us say AB, the bolt cross sections. Now, this will be the minimum cross sections, that is at the at the root of the thread, times sigma tension allowable. Now, this is equal to, again, sigma tension allowable will be equal to SY divided by some factor of safety. Now, knowing all this, we can find out the AB. Now, there is another way of failure, that is by the crushing of the bolt. How does it occur? Let us see. The bolts, no, so if the forces are on each of the bolt, the force is, let us say, small f, then the total crushing area will be this projected area. There are n such projected areas, and this will be equal to n times d of bolt, that is the bolt diameter, times the length of the Tf, the flange thickness, TF. So, this is the overall the total, this is the total force and this will be the area. So, therefore, the total shear the stress will be N times dB times TF and that must be less than equal to the sigma bearing stress, and sigma bearing stress will be equal to about twice that of S of, that is SC is the yield stress in compressions divided by factor of safety and roughly twice of that. And so, this is the F, and now F is again, if you assume the entire force is distributed here, it will be T divided by this radius of the bowl circle, that is d1 by 2. So, using this formula we can calculate the dB, that is the bolt diameter. Now, this is how the bolt diameters are selected. Now, what happens? What happens when there is no clearance? Then of course, the failure mode will be the shear across this surface. So, now the shearing force, the total shearing force will be tau, this is the maximum shear stress, this is tau max, times the total shearing area, it will be equal to times N times this area AB. This is the total shear force, and that is when multiplied by d1 by 2 should give T, the torque transmitted, and therefrom we may calculate AB. Now, the tau allowable, that is tau max, will be equal to, it is normally taken to be 0.6 times Sy by Sf, that is 0.6 times the allowable tensile stress, which is equal to yield stress divided by factor of safety, roughly taken to be 2 to 3. This is how the bolts are designed. Then what are the other important things? The other important things will be this half diameter, which is which was named D1, D2. Now, how this is calculated? This is calculated based on the principle of shear the shear stress due to torsion. Here you see, if you consider this half to be a hollow cylinder, then the total shear stress will be equal to the torque transmitted times the maximum shear stress here on this surface is equal to d 2 by 2 divided by pi by 32. Now, outside diameter to the power 4, that is d2 by 4 minus d by 4, and this must be less than equal to tau allowable. So, this is how we may design the D2. Now, sometimes we have to check for the design, that is the design data are already there, we have to check. Now, you will have to use this formula in order to check the safety of the design. Another thing is this TF. Let us see how to calculate that. Now, the TF, when you take this part of this flange, then So, this is Tf. Now, the total force on this side will be equal to, let us say we assume that the total force is F. Now, that divided by the area will be the shear stress. The total area is pi times, let us say here. So, pi times d2, always say d2 is here, pi times d2 times Tf. This is the shear stress, and that must be less than tau allowable, and again F is related to the torsion by this formula, that is d2 by 2. So, if you use these two formulas, then you can find out the safe value of Tf. Now, this is how the flanges are designed. Now, come to another type of coupling, which is known as slip or muff coupling. Here what you see is the shaft, this is the part of the shaft, and there is a rigid slip attached on the top of this shaft, and these are fixed by means of a key, what you see here, and this key may be of different types. What you see here is a give headed shank type key, but there may be other kinds of key, for example the Woodruff key, or the pins may be there, or what you have already learned in screw, that is there may be set screw also used in connecting the slip to the rod. Now, normally there are two situations. The this muff or the slip is put on the top of the shaft by means of press fit or interference fit, or by means of keys. Now, oftentimes the both interference fit and the keys are used. Now, what you see here, the usual design data d, which is the outer diameter of the slip, is equal to 2 times d plus 13 millimeter. Again, this is again taken from the standard, and L is normally taken to be 3.5 times the diameter. Now, what will be the important design criteria here? Of course, the first design criteria will be that the stresses in the key, if the key is the main load bearing member. Sometimes keys are not main load bearing member, but the torque is transmitted by the friction force generated on this surface. Here the friction force is generated because of the interference fit. Then there may be the stresses in the sleeve itself. So, there are few design criteria which we have to see. Now, let us look at the design criteria of slip coupling. The first one, let us consider that the slip is put over the shaft by interference fit, and then what happens? Then of course the stresses will be developed in the slip Now, this is the outer diameter d, and this is the inner diameter, which is equal to, this is that of the sleeve, and this is the inner diameter, that is that of the shaft, and this is small d. Now, this is the slip. Now, whenever there is interference fit or shrink fit, then there will be the pressure developed. Then because of this internal pressure, there will be the stresses developed, and the stresses may be calculated by means of Lamè's equations, which you which is sigma r, that is there will be both radial stress and circumferential stress. So, if you draw sigma r and there will be sigma theta. So, there will be both radial stress and circumferential stress, and those are given by this formula, that is C2 divided by r square, and sigma theta is C1 plus C2 divided by r square. So, they vary in inverse proportional of r square. Now, when we use the boundary conditions, suppose it is subjected to pressure in the inner surface. So, the boundary conditions will be definitely sigma r will be equal to minus p if the p is the pressure at r equal to Ri, which is equal to d by 2, and sigma theta will, well, the boundary conditions will be now not in terms of sigma theta, but every time in terms of sigma r. So, sigma r will be 0 at r equal to d by 2, that is there is no pressure applied at the outside surface, whereas there is the pressure P which introduce a compressive stress at the inner periphery. When you use this, then you get the value of C1 and C2 in terms of P. Now, whenever there is interference fit, then the problem is little complicated. There what you get is, you cannot get P directly, but you will have to use the kinematic relationship. So, in case of interference fit, we have to use the kinematic relationship, that is, suppose the initial difference between the shaft and the slip, the diametric difference, let us say delta. So, after the shrink fit, the radial deflections will be delta by 2, and this will be equal to U2, that is, if we consider this is material 2 and that is material 1, then U2 will be the deflections, the radial deflections of this point minus U1. So, this difference will be equal to delta by 2, and again you know epsilon theta will be equal to U by R. This is known for axisymmetric problem, and of course we know that sigma and we know that this will be equal to 1 by E epsilon sigma theta minus nu sigma r. So, this is a generalized Hooke's law. When you use all these equations, then you get the following thing, that is, the pressure will be equal to delta E by 2 internal radius times 1 minus d by d square. So, from this we get the value of P. Now, once this P is calculated, that is, knowing this value we can calculate P. Of course, here we have assumed that these materials are the same, that is, they have the same Young's modulus and Poisson's ratio. Then this P once known, then we can calculate the torque transmitted. The total force on the circumference will be equal to P times mu, and the area, that is equal to pi times d times L, the length of the slip. This is the total force times d by 2, and that will be equal to the torque. So, this is the torque capacity of such a slip, that is such a coupling. Of course, from here we can find out various things, that is we can find out the bursting pressure inside sigma theta and sigma r etc., knowing this P and knowing this Lame's equations, and this sigma r and sigma theta must be less than some limiting value or allowable value. Now let us come to the situation where the keys are the main load bearing member. So what I am drawing here, half portion of such a sleeve, so this is the half of the sleeve. Here this is the key, is the main load bearing member. Now you have to calculate the design, that is the width and height of the key, but this I leave that to you because now you know how to design such a key. Once the key is designed, then we have to check for the pressure or the stress inside the sleeve. What you see is that there the stresses will be developed. Here we have the pressure which is transmitted from the shaft through key to the, from shaft to key to the sleeve, and that causes a tensile stress over here. So whenever such a situation occurs, then there is a possibility that it may break from this point. Now we have to calculate the tensile stress. What will be the total force? The force, let us say we calculate, the total force will be equal to F, and if it is uniformly distributed, if we assume that this force is uniformly distributed, then the equivalent point of applications of this load is here, which is, let us say, this distance. If this height is 2h, then half of the height is there. So this distance will be equal to d by 2 plus h by 2, and that will be equal to torque. Now this is how we calculate F, and the stress will be, stress over these sections will be then sigma is equal to F divided by this area, and that will be equal to the length of the sleeve times this length, which is equal to x say, and that must be equal to less than equal to sigma allowable. How to calculate x? That comes from plane geometry. What you see here, suppose the width is w, then you can find out if this diameter is, let us say, capital D, then what you have is x will be equal to, now that you can easily find out, this will be equal to this is D, so D by 2 square minus W by 2 square minus H minus small d by 2 square minus W by 2 square. So this is how we calculate x. That is plain and simple if you consider two triangles, two right angle triangles here, and then this equation comes automatically. After having calculated this value, you can check for the stress sigma, and that must be less than this allowable stress. So this is how we have to check. The other stress, of course, which is very important, will be that of the shear stress. And again, here the shear stress, if you consider the torque, then the torque distribution will be equal to, here the maximum torque is T, and that occurs in that sections, and in that case the shear stress will be T times the maximum shear stress will be d by 2 divided by pi by 32 d square minus d square, and that must be less than equal to tau allowable. So, this is how we calculate the stresses in a slip coupling. Now, we come to another type of coupling known as the clamp coupling. This is sometimes called the split muff coupling also. Here instead of using one single piece of slip, we use a split slip, that is, it is made of two parts and they are now connected by means of few bolts. As you see here, this is made of two parts and they are connected by few bolts. Then there are ribbed arrangement in order to give additional strength. Now, here the design parameters which you see here, this will be the same, almost the same as that of the slip bearing slip coupling, and the length is also the same. But what will be the important design parameter here? The design parameter will be definitely the failure of the bolt, which here the bolts may fail. So, we have to consider the failure of the bolts, which we do now. Now, let us consider the part of the slip, and we have bolt here. Now, let us assume that each bolt is given a force, a clamping force F. So, if there are n such bolts, then the total clamping force will be N F, and this is supported or balanced by pressure developed. So, the pressure will be equal to the projected area times the uniform pressure. So, projected area will be d times L, the length of the sleeve, times P. So, this is how we calculate P. Now, if you assume uniform pressure, then of course, the friction force will be equal to mu times the pressure, and that will be also uniform. So, the total frictional force will be equal to mu times P times the area, that will be equal to pi by 2 times d times L. So, this is the total force times d by 2 will be equal to torque. Now, this is from one side. So, you will have to calculate, you will have to use factor 2, because there is another slip, half slip appearing here this side. So, therefore, we have to multiply a 2, but in order to have a safe design, we neglect this 2, because we assume that half of the bolts carry the load, and that is a safe design. So, from this, when you substitute P here, then you get F in terms of T and other things, D, etc., etc. So, you get everything in terms of T, and if F is a bolt times the sigma allowable, that is the, this is the allowable force, the maximum force available. From this we calculate the bolt diameter looking up at the table. So, this is one such example of the torque transmitted by the friction, as you see here. Then of course, the other forces or other stresses in the members will be same as that of the slip bearing, which we are not going to say right here. We now come to the next type of coupling, which is known as the compression coupling. Here the methodology is that we use the principle that whenever we insert a wedge, then it develops a large frictional force. So, that advantages of wedge is taken help of here. What you see here, this is the cone type sleeve, you see the cone, and this is the shaft, and this will be a double cone type. These are again split types of cones, but they are wedge. So, they have a wedge actions, and the axial force to this wedge is given by tightening the bolts. The bolts are made square cross sections in order to have a larger tightening force on the nut. The usual dimensions are written here. This radius, that is the innermost radius of the cone, will equal to about 1.5 times d, whereas the outermost radius of this wedge is about 1.8875 times d, and the final, that is the outermost radius, is 2.585 times d. So, this is one such coupling which is known as Seller's cone coupling. Then we have another kind of coupling, this is known as flange type or ring type coupling. What you see here is a flange type coupling. You see here we have a continuous sleeve, but this is not straight, but this is made a little conical, and there are flanges put on top of the sleeve, but these two have again the conical surface, and again these two flanges are tightened by means of bolts. The design will be, the bolt design will be same as that of the flange coupling, but here you will have to consider the force transmitted because of the wedging actions here, as you can always guess. So, this you have studied in your mechanics class, I am not going to derive it here. Another way of applying the coupling is to have such kind of couple, the cone type muff or sleeve, and then two rings are put. Again by interference speed we develop a large pressure here, and that usually transfers the torque from one shaft to the other shaft. Now, this is quite advantageous when we use in the outdoor conditions where there may be environmental hazards, it may be rusted the whole coupling. So, it will be very difficult to disassemble them. If you use such kind of coupling, then it is quite easy to disassemble the entire shaft and the coupling. So, these are the one of the advantages of the compression coupling, ring type compression coupling. Now, we come to one of the very important factors here, that is the service factors for typical machines. What is meant by service factor? Now, every time I designed with a constant torque, and how to rate this torque? This torque may be rated from the diameter of the shaft. So, this is the maximum torque which could be transferred, but usually it seldom happens that the torque is constant, because the shafts are used to drive various machines. So, there will be definite some fluctuations of the torque. So, the total torque will be equal to T fixed torque, that is the static torque, plus T dynamic torque. So, this T dynamic torque varies from machine to machine, and we have to take this as a factor here on the static torque. So, whenever we have a static torque, that is, this is fairly known, then we have to multiply by this factor. And how to derive this factor? Again, these are derived only from the previous experience. So, this is known as the service factor. Let us see the typical service factors. Now, machines with small accelerated masses, here you see the service factor is 1 to 1.5. Then the medium masses and variable load, that happens in, for example, in piston compressors, in planers, in grinding mills, and the service factor is taken to be 1.5 to 2. Then heavy masses and shock loads, here the service factor is 2.5 to 3. The usual machines where this heavy masses and shock load occur is some examples are power hammers, rolling mills and ball mills. So, there are various other machines also available, and these are fairly tabulated, and the coupler manufacturers, they provide all this data. So, whenever you have to select the coupler, then you will have to look for the typical service factor. If the machinery is now powered by IC engine, then K is increased by 20 to 40%. Now, that is very important, because IC engines, all of you know that the force or the torque transmitted by IC engine is very irregular. For example, in a 4-stroke engine, we have in one stroke there is a large compressions. So, there is a large power stroke, here the force is very large, and in another stroke there is a small force also, but in 2 other strokes there are practically no force. So, therefore, whenever we have IC engines, then the fluctuations in the torque is very large. Therefore, in case of IC engines, we have to increase K by a factor of 20 to 40%. Now, the larger value being for small number of cylinders. Whenever we have multiple cylinder IC engines, then that fluctuations could be little bit reduced, and that is the advantage of multi-cylinder engine. Whenever we have multi-cylinder engine, then the power strokes happen in one cycle. In 4-stroke there is one power stroke, but now for n cylinders there will be n such power strokes. So, the distribution is little bit even. So, whenever we have larger value, then we that happens for small number of cylinders. Now, let us see some of the disadvantages of the rigid couplings. Now, the first disadvantage, as you see, is no provision for shaft misalignment. So, since these are rigid, then if this is the coupling, then here suppose we have a shaft and this is coupled here, another shaft suppose initially here, then when we connect it gets bent, as you see very well that gets bent, and therefore, whenever such cases occur, then there is a huge bending stress developed. So, there is a huge bending whenever the shaft is misaligned. Hence, rigid coupling is not suitable whenever there is a large misalignment. The second is that the large bending stress. Large bending stress, here you see, take for example a beam which is supported on two such simple supports, then of course, there is no bending stress here, that is from the conditions kinematic relationship of such kind of support, but a rigid coupling is taken to be a fixed clamp. So, therefore, whenever we have rigid coupling, then there will be a large bending stress develop. If you compare this with a cantilever beam which has again fixed end, then you see the bending stress will be maximum here, right. So, large bending stress is developed. The third point is that shock and impact loads get transmitted. That is very important, because sometimes shock appears in one machine, for example, which is connected to one part of the shaft. It should not be transferred to the other shaft. So, coupling should have adequate flexibility in order to restrain this impact, but a rigid coupling cannot restrain this impact. Let us see, if you have one mass and a flexible object which has flexibility, that is stiffness k, if you have this force F0 cosine omega t, that is a variable force with a frequency omega, then you see the total force transmitted on the other side, that is on the base, will be k times the displacement, and that will be equal to F0. If you calculate, you get F0 divided by 1 minus omega by omega natural square, where omega natural is the natural frequency and the omega natural square is k by m. So, whenever we increase this omega, then we see the entire force, whenever we see omega n, we increase omega n, then this becomes very, very small. So, the entire force gets transmitted to through this side, whereas if we have a small value of omega n, then of course, the total force transmitted will be very, very small. So, this is one of the advantage of a flexible member, that is, if we have a large variable force here, then the transmitted force will be relatively small if the flexibility is properly chosen. But we have to avoid one condition, that omega should not be near equal to the omega n, where the force transmitted is very much increased. So, these are the disadvantages, and these above disadvantages can be reduced to some extent by flexible couplings. So, there are few kinds of flexible couplings, but we are not going to discuss today, we postpone it until the next lecture. So, for this time being, I take leave. Dear student, let us begin the lectures on machine design part 1. This is lecture number 21 and the topic is shaft coupling. This is the concluding lecture on the same topic. So, before going to the subject proper today, let us recapitulate little bit what we have learned in the last lecture. We talked about the couplings. Now, couplings are used to connect two shafts for relatively long time. And there are primarily two types of couplings. One is rigid coupling. As the name suggests, the coupling is made of a rigid material. There are few kinds of rigid couplings which we discussed, namely flange coupling, which is the common type of coupling, then sleeve or muff coupling, then we discussed clamp coupling, and then compression couplings. But towards the end of the lecture, we mentioned that there are few disadvantages of the rigid coupling. So, we are going to start from that point today. Let us look at some of the disadvantages of rigid coupling now. First, no provision for shaft misalignment. Now, I want to emphasize here that shaft misalignment, there may be few kinds of shaft misalignment. One may be here one shaft, another shaft here, So, there is a parallel offset, maybe shaft one here, another there. So, this is angular offset or angular misalignment, and there may be a combination of both, that is there may be an offset and angular mismatch. So, these are the three basic types of misalignments, and the rigid couplings are incapable of providing for these misalignments. Then large bending stress develops. Whenever there is misalignment, if you want to bring the shafts together, then a large bending stress is developed, and that is detrimental, because when the shaft runs, then it leads to the fatigue loading, large fatigue loading also. Again, if we attach the rigid coupling where there is a large bending moment due to various other reasons, then also the bending moment is quite detrimental. The last point, and which is very important, that is shock and impact loads get transmitted. So, the rigid couplings are not capable of providing any cushion to the shock or impact loads. Now, the main point of departure today will be the flexible couplings. Now, these above advantages can be reduced to some extent. You will see after today's lectures that what are the extents by flexible couplings. So, let us now come to the flexible coupling. Now, there are few types of flexible couplings. One is the couplings with kinematic flexibility. That is, the flexible members or the flexibility of the coupling is made by having some kinematic pair inserted between. So, depending upon the kinematic pairs, the couplings may have different kinds of flexibility. One type is cross sliding coupling. Here we use two prismatic pairs. Universal joint, which uses spherical or special mechanism. Gear or tooth coupling, this is again a higher pair mechanism, and chain coupling, which consists of large number of revolute pairs. So, it leads to a large flexibility of the coupling. Then couplings may be of resilient members. Now, here the flexibility is brought in by with the help of the members which have their inherent flexibility. Now, the most often used flexible members are elastomers, that is